In episode 1, bisection needed about 20 iterations to pin that root. Newton-Raphson does the same job in 4. How? That's what this episode is about. Welcome back to Numerical Methods, episode 3, the Newton-Raphson method. First, why do we need something new? Bisection only ever asks one question. Is f of c positive or negative? That's a single bit of information per step. It throws away everything else the function is telling us. But f has more to say. At your current point, f also has a slope, a derivative, that points towards the root. Use that slope and you can take bigger steps and aim them in the right direction. Here's the whole idea in one picture. This is our curve and the root we are chasing is where it crosses 0. Call the true root x star. Start with any guess, call it x naught. Draw the tangent line to the curve right at that point. Follow the tangent down to where it crosses the axis. That's your next guess, x1. Already much closer to the root. Now just repeat. Tangent at x1 slide down to x2. Each tangent is a straight line shortcut aimed at the root. Tangent at x2 down to x3. 3 steps and we are essentially on the root. Let's turn that picture into a formula. Take the tangent at the current point xn. Its slope is f prime of xn. So the tangent line is y is equal to f of xn plus f prime of xn into x minus xn. The next guess is where that tangent hits 0. So set y is equal to 0 and solve for x. Move the terms around, isolate x, and you get xn plus 1 is equal to xn minus f of xn over f prime of xn. That's the Newton-Raphson formula. Here's the algorithm in full. Pick a guess, step along the tangent and repeat. Step 1. Pick a starting guess x0. In step 2, compute the next iterate. Xn plus 1 is equal to xn minus f of xn over f prime of xn. In step 3, repeat until the change is very small. That update line is the heart of the whole method. When do you stop? A few common criteria. Stop when consecutive iterates barely move, when f of xn is essentially 0, or after a fixed cap on steps. In practice, the relative change is the safe default. But notice the catch. Newton needs the derivative f prime of x. That's the price of the speed. Let's run it for real on f of x is equal to x cube minus x minus 2 with f prime of x is equal to 3x square minus 1, starting at x naught is equal to 2. It's the same function bisection chewed on in episode 1 for a fair fight. Here's the curve. We start at x naught is equal to 2. Iteration 1. F at 2 is 2 cube minus 2 minus 2 which is 4. That's our height on the curve. The slope there, f prime of 2 is 3 times 4 minus 1, 11. Draw the tangent with that slope. x1 is equal to x naught minus f of x naught over f prime of x naught. That's 2 minus 4 by 11, which is about 1.6364. The tangent lands here at x1. One step and we are already close. Iteration 2, f at 1.6364 is about 0.7453. Up to the curve again. The slope there is about 7.0331. New tangent x2 is 1.6364 minus 0.7453 by 7.0331. It is about 1.5304. Land at x2, closing in fast. The rest fits neatly in a table. Here it is. Step 0 to 4. 2, then 1.6364, 1.5304, 1.5214 and 1.5138 and watch f collapse. 4, then 0.75, 0.05, 0.0004 and about 10 to the minus 8. Bisection took 14 steps to guarantee 10 to the minus 4. Newton reached 10 to the minus 8 in 4. Same problem, different league. Here's the key insight. Each Newton step roughly squares the error. So the number of correct digits doubles every step. 1, then 2, 4, 8, 16, and so on. That's why 4 Newton steps beat 20 bisection steps. Let's make fast precise. Newton comes with a different kind of guarantee than bisection. The next error is bounded by a constant times the current error squared, where En is how far xn is from the true root x star. It holds under three conditions. F is smooth near the root is simple, f prime isn't zero there, and you start close enough. Y squared. Taylor expand f at the root, divide by f prime of xn, and rearrange. The error comes out proportional to the previous error squared. In practice, that squaring means digit doubling. Watch the error fall 10 to the minus 1, then minus 2, minus 4, minus 8, minus 16. It roughly squares each step. Newton is fast, but it isn't bulletproof. Here's when it fails. Speed has a price. There are three ways it can blow up. Failure number one is a horizontal tangent. Take f of x is equal to 1 minus x square and pick x naught is equal to 0 right at the peak. There f is 1 and the slope of f prime of 0 is exactly 0. A flat tangent never crosses the axis, so Newton's step divides by 0. It's undefined. Failure number 2 is a bad starting guess. Here's f of x is equal to tan inverse of x. Its only root is at 0, but we start out at x naught is equal to 1.5. That's the target root in green. The first tangent overshoots, landing at about minus 1.69 on the far side. The next overshoots even more, out to 2.32. Each step lands farther out, x3, x4 and beyond, race off to infinity. The iterates diverge completely, a bad guess and Newton runs away. Failure number 3, the sneakiest, is cycling. Take f of x is equal to x cube minus 2x plus 2, starting at x naught is equal to 0. The tangent at 0 lands at x1 is equal to 1. So far so good, we have moved to 1. But the tangent at 1 sends us straight back. x2 is 0 again, exactly where we started. And x3 is 1, x4 is 0 and it keeps oscillating between 0 and 1. Tangent at 0 lands at 1, tangent at 1 lands back at 0. An infinite loop. So bisection is slow but bulletproof. Newton is lightning fast when it works. Use a good initial guess or better yet combine the two. Exercise 1. Use Newton to estimate square root of 3. Take f of x is equal to x square minus 3. Start at x naught is equal to 2 and compute x1, x2 and x3. Pause here and work the three steps. Here's the run. From 2 you get 1.75, then 1.7321, then 1.73205008 and f drops from 1 to 0.06 to 0.0003 to about 10 to the minus 9. x3 matches square root of 3 to 8 decimal places. 8 correct digits in just 3 steps. Exercise 2. Apply Newton to f of x is equal to x square minus a in general and simplify the update as far as you can. Pause and simplify. With f of x is equal to x square minus a and f prime of x is equal to 2x. The update becomes xn square plus a over 2xn, which tidies up to xn plus 1 is equal to 1 half times xn plus a over xn. That's the ancient Babylonian square root method. They were running it in 1700 BCE. Newton just showed us where it comes from. Exercise number 3 is a challenge. You run Newton on f of x is equal to x cube minus 5x from x naught is equal to 1 and it refuses to converge. Why? Pause and compute f prime of 1. f prime of x is equal to 3x square minus 5. So f prime of 1 is minus 2. Then x1 is 1 minus 5 over minus 2, which is equal to minus 1. And x2 is minus 1 minus 1 plus 5 over minus 2, which is equal to plus 1. You are trapped in a 2 cycle, bouncing between 1 and minus 1. It's failure mode 3, cycling, striking again. And that's the Newton-Raphson method. Thanks for watching. Newton steps along the tangent. Each step squares the error, so the correct digits double, but it needs f prime of x, and it can fail without a good guess. Next episode is the secant method, Newton's speed without needing the derivative. Like, subscribe, and tell me your favorite failure mode in the comments.